So now we come to the keynote session of this afternoon. We will warmly welcome Professor Sotirios, and he is from University of Edinburgh. He is a canon medical and a Royal Academy of Engineering Research Chair in Healthcare AI. Professor Sotos is currently the the chair in the machine learning and computer vision at the University of Edinburgh. He is also a Turing Fellow with the Alan Turing Institute and an Alice Fellow. Previously, he held faculty positions with IMT Institute for Advanced Studies, Lucca, Italy, and Northwestern University, USA. He has published extensively, particularly in interdisciplinary fields, with more than 180 journals and conference papers in his active record. His research interests are machine learning, computer vision, and image analysis. The title of his talk is Diffusion Models in Medical Image and Analysis, Hype or Hope. Let's welcome Professor Sotirios.
Hi, everybody. I hope you can hear me okay.
Yes? Yes.
Okay, great. Thank you. So everybody calls me Sotos. Thank you for this kind introduction, and my apologies for not being able to be there with you today. So I'll start by sharing my screen to the best of my ability. I think I should be able to still remember how to do that. You should be seeing a blank screen, and now, and you should be able to see the presentation. Is that okay now?
Yes, it is okay.
All right, thank you so much. And I'll get started. So as the kind introduction, the introducer said, I'm Sotos, and I'll talk to you today about diffusion models. Before I get started, I would like to thank the organizing committee for inviting me, and also Jenny for all her support as of now. And thank also to Pedro, one of my PhD students, for helping me put the presentation together, and all the colleagues, as you will realize soon, that have set slides in trying to put this thing together. So I'm here at the University of Edinburgh, and I lead the group called VIOS, where I call it that we do interdisciplinary AI. We're trying to think of what sort of problems can inspire the need for new algorithms in AI. And we particularly focus, of course, in healthcare, but also in applications where we see that we need AI algorithms that can do more with less data. So why are we talking about diffusion models? And I'm sure you probably have heard about all these new fancy text to image generative models. So you probably have seen, let's say, Stability AI with their stable diffusion, where you can write a small text and actually get a very high quality synthetic image. The same thing was done by Google Brain with their model Imagen, or DALI by OpenAI. We see an evolution of generative models that have actually increased the quality and the diversity of the samples that we can get. So, but why with diffusion models, and what is diffusion model? And, diffusion models are not new. Actually, they originate from score-based models that were invented very early on. Even if you're familiar with restricted Boltzmann machines, these are also score-based models. But in the last few years, diffusion models have witnessed an explosion. So since 2015, where we had like maybe on average few papers per year, suddenly we have about 600 papers mentioning diffusion models and machine learning from arXiv. And 36 of those, of the last, let's say, year alone, where we had about 400 new papers, 36 have been in our field. So this talk is going to try to at least give you a flavor of those 36, but not all of them in the amount of time that we have allowed. So, but before I get started, I will tell you just a very tiny introduction about what diffusion models are, and then we will proceed to see these examples. So what are diffusion models? So first of all, let's talk about what are generative models, okay? So generative models have the task of, let's say, given some data, okay? And this data come, yes? Okay. The data come from a data distribution. Our goal is to, given a model family, to learn the parameters of a model that we are able to match using some metric to minimize the discrepancy between the true data distribution and the estimated data distribution. So we use the word model family. So models, generative models, can probably you have heard of them as VAEs, GANs, normalizing flows, and the most recent flavor of the one I'm describing you today is the diffusion model. So overall, generative models can be seen as those that are based on likelihood estimation and those that are other implicit. Typically, likelihood models such as VAEs, flow-based, and so on, they require inductive biases as a way to ensure a tractable normalizing constant as they estimate for the likelihood computation. Or they will use surrogate objectives as a way to approximate maximum likelihood trading. Like the classical in the VAE is the evidence lower bound, the elbow. On the other hand side, implicit models like a GAN, they have this kind of like adversarial game, right? So you have a discriminator and a generator. And as we know, or you're familiar with, this can somehow tend to be unstable and can also have mode collapse. Diffusion models bypass these limitations with several neat tricks. So, and one of the fundamental things that diffusion models rely on is the idea of the score. Okay, so what is the score? So imagine that we have some data, all right, in some high dimensional space, and we ask the question of like, how can I really generate this data? How can I learn the distribution? One simple idea, well, simple is kind of an oversimplification, is to say, well, what if I start here with random noise somewhere here, and then I ask what sort of steps do I need to do such that I can arrive within the vicinity of those points? Okay, so if you see this graphic, this GIF is from Yan Song. So we start with random noise, and slowly we move until we are able to match the data distribution all the way down here. Okay, so we learn how to iteratively modify an input until we arrive at the data distribution that we want. So we start with random noise and iteratively move towards that. Now, the diffusion models essentially learn the gradient of the log probability of the data with respect to the data themselves. So if you notice here, the gradient is respect with x. So we are essentially learning the update that we need to do to points as a way to match the data distribution. How do we do that? So this is another of the neat trick, okay? So they approximate the score by doing a denoising step, okay? So I'll take a few moments here to explain this a little bit better. So let's say we have some input data, we draw some random noise, and then we add this random noise together in a convex combination, right? So we just add the scalar factor there, and we create a new input. Then we give this to a neural network, and we ask the neural network to predict the noise, okay? So, and then we use a mean squared error there as a way to estimate how well have we predicted the noise, and use this mean squared error as a way to update the parameters of the neural network. To help the neural network, we give it some extra knowledge. First of all, we use this parameter t, which means the diffusion time, where we say that, and we give the neural network, like we are now a diffusion time step, the value t equals, let's say 0, or 2 equals t equals 1. And we randomly draw this t. So what we do to train this, we take the noise, we draw a t, we draw alpha t from a schedule, we create the noisy input, and then we ask the neural network to predict the noise. Okay, and we do this at random, and this t will vary from 0 to t. And as you can see, we start with basically a very clean version, but the more we increase t, the more noisy this version becomes. And during this basically simple denoising process, the neural network has learned the structure of the data, and implicitly actually has learned the data generation, how to generate data. So, but it's kind of crazy, right? So how can this be used to generate data? So inference happens in an even more simple manner. So you start with the largest value of t, you start with complete noise, you are conditioning the model with t, and you're getting another version of the output, the denoised version. Then you subtract it from the input, you lower the value t, and then you do it again, again, and again, and again, and again, and again, until you're actually getting the desired image that you want to obtain from the output. So you start with complete noise and iteratively change it until you arrive at the desired image. So now you will say, well, I mean, okay, sounds okay, sounds like a denoising, but how can we can explain this explosion? So I think the one of the easiest way to explain the practical explosion of diffusion models is they're able to reuse some of the classical things that we have already learned very well how to do. So how do we, for example, use units, transformers, VQVAEs? We are using all of the state of the art in what has been done in machine learning until now. And at the same time, we also use another technique called conditioning, which we are able to modify how the neural networks behave by altering the values of their features directly. So in the next few minutes, I would like to describe some of the examples from the community and how we have used it we and others have used it in medical image analysis and medical imaging tasks. So one of the most populous one has been, as of now, image reconstruction. So if you think in the context of CT, you're obtaining these measurements Y and you're asked to invert it and obtain the image X, right, to reconstruct. The same thing can happen in MRI. Both both work in a different type of like space, but the whole idea is the same. So how can I be able to learn a model that can do the inversion from Y to X? So there's been lots of different types of work here, but I'll pick an example here from the university, Bilkent University, from Tolga's group, where they used a diffusion model as a way to learn a prior of how high quality looking images look like. So here the prior is used to train in a paired fashion between, let's say, measurements in MRI, for example, in K-space, and the desired high quality output. So there is a nice very trick that they do here where they check whether the data during reconstruction conform to the data model. So they look at, if I downscale it and I do the K-space, do I able to obtain the original measurements? So this kind of like adds a data consistency as a way to make it more appealing and conform to kind of like the test time data. And if you look at the results, they're very impressive, and they have additional experiments within their paper if you want to follow it. But overall, we see that particularly for the area of reconstruction, the denoising networks and diffusion models have been very, very popular. Now, another popular and I think ready-made application for generative models is image synthesis. So can I learn, for example, how to create synthetic data by looking at how real data are, right? So, and without surprise, of course, several people have tried to do that. Here, I'll pick a couple of examples. The first one is from Walter from King's College London and Jose Cardoso, where they try using the UK bio data, they use a latent diffusion model. So a latent diffusion model is a diffusion model, but rather than operating directly in image space, it operates on latent space. So you learn an autoencoder of the data first, and then you train a diffusion model. So you cannot compress the information a bit. So, and they're able to learn this generative model by also conditioning on covariates such as like age, gender, other characteristics of the brain. So you can bespoke create data that you like. And they released, interestingly, a data set with 100,000 synthetic brains as a way to enable research on data that other people may not be able to have access to. Interestingly, another paper by FAO in Germany, they said, well, how do we know that the generated data do not really look alike than one of the real training data, right? So they have here a very interesting approach where they will say, I will get some original training data. I will learn some synthetic data here. This is in X-rays. Then I will have a step where I'll check whether the generated data are too close to some of the data that I have in the training set. And if they are too close, then I exclude them. But if they are different, I'll keep. And the whole idea is to show that you can train classifiers without having access to the original training set, in some sense, in a privacy preserving manner. And they showed that diffusion models can do much better than other models like progressive GANs here compare and come as close to using the real data for training a classifier. And if you look at even the images, they look actually very, very nice and very highly in fidelity. This work from Tolga's group again in Bilkent, they went ahead and say, well, we can do image synthesis by starting from noise, but we can also start from another image and say, can we modify this image to become part of another modality? So this is known as image-to-image translation. So they used here, they wanted to come up with a model where you can do image-to-image translation in an unsupervised manner. And they use some interesting tricks. So because you don't have pairs of the same datum, let's say the same patient in both modalities. So they have two separate loops and a cyclic kind of consistency loss as a way to enable to go from one modality to the other. So there are discriminators involved in the non-diffusive model, but then the interesting key here development that they had in this paper is that there is a diffusion model that does the mapping between the source and the target very fast. Because if you recall before, the diffusion models have an iterative process to generate data. So they wanted to be very quick, and they were able to radically reduce orders of magnitude how many steps are required as a way to do the synthesis. And if I show you some of the visuals, are very, very appealing. I mean, the quality is already very, very high. Now, naturally, you would think that image-to-image translation, between different modalities should also appeal to be able to do image segmentation. So can I go, for example, from images to the segmentation? That's kind of like another image-to-image translation task. So one of the papers here that I'm presenting is by Julia and Julia Wallab. So the main idea here is to learn a joint distribution of masks and images. But rather than thinking of having the images as an input, you start from noise. So you're learning actually a distribution of masks conditioned on the images. Okay. So you can see we start from random noise and we're asking to create a denoised version of the mask but by conditioning here with the input. Okay. And the way they do the conditioning, let's just concatenate here this noisy version of the mask with the images that they want to use as an input. But what's the benefit of here? If you notice, we are using different types of noise. Okay, so this means for different type of noise, keeping these images fixed, I can get different segmentation results. So I get an ensemble of results, right? And this means that if I take their average, their mean, I can get maybe a denoised version of the mask, so I can get an even better improved performance, denoised by averaging, not denoised by the diffusion model. And if I take the variance, I have an estimate here of the uncertainty, and maybe that can help with some other downstream task. But all of these things require pairs. So a work by Younger from KAIST, they have here a very interesting approach on how you can use diffusion models coupled with discriminators as a way to segment vessels in angiographical images without label data. The process is slightly complicated to explain very quickly in 1 minute, but overall, they start with two different paths. You have a path that you start with an image and your goal is to obtain its segmentation, or another path where you take two images, one image that is a generic background and something that looks like a segmentation but is completely synthetically created and is conditioned here via injection to create a realistic looking image and a realistic looking mask. So the way they do that is they use a spade layer. Spade is a conditioning mechanism that was invented a few years ago as part of the synthesis literature. Okay. So, and they've run several experiments here on several different data sets, and I must admit the results are very impressive. And they showed lots of robustness to noisy data, and they show that they are able to generalize to external data, but also cross-model data from retinal imaging. The same group have also done some work on image registration. And its image registration is not very popular, but this work from Young is very, very interesting as well. So you have here two image pairs. Let's say you have a moving image and a fixed image, and your goal is how to change the moving image to make it match to the fixed image, right? So they do image registration along the continuous trajectory. So you have a diffusion network here that predicts noise, and then a deformation network that predicts the deformation of how you should change the moving image to match the fixed image. Very interesting algorithm with using the kind of like the diffusion network to learn the distribution of the parameters of the deformation network, and then the deformation actually network doing the registration and providing the deformed image. I won't go through the loss function, but the paper has a very good detail also on the algorithm side. Most interesting here, I presented the results on their 3D cardiac MR image registration in intra-subject, where they basically try to correct for the motion in the heart, and they compare it with other methods as well, and they show considerable performance improvements, which is, has several applications, particularly as we estimating cardiac deformations, wall thickness, and so on. Another area where diffusion models have been very popular is in anomaly detection. Anomaly detection is pretty simple as an idea. So you get some original data, you're putting it through a model, and you hope that if you have learned well the distribution of how normal looks, right, that reconstruction will not include where the disease is, right? So by subtracting them, you're able to obtain a heat map of where you think there is abnormality, and this should be enough for you to do a ground truth delineation of the abnormality or its detection. So I'll present here as an example a work by Walter from KCL, where again they use this latent diffusion model where you get an image X, you obtain some compressed representation from a VQ VAE, and then you learn a diffusion model to go to do the classical process of the diffusion model, right? But so you don't operate in the input images, but you operate in the space of latent features. So the good thing with that is that basically through this encoding process and the diffusion process, you identify regions with low likelihood of belonging to the healthy part, right? And as you do the inverse process going from here to here, you are essentially, if you can see in this video slowly, you will see now that it will start clearing up where the disease is. Like you started with the disease and slowly as it iterates, it cleans it up. So it heals it by painting these regions. So this model used only healthy data to be trained. But what if you have some additional information? What if you have some weak supervision? So you might have, let's say, data that you know are healthy versus other data that you know that are unhealthy, but you do not know the segmentation. So you don't know exactly where the disease is. Could you somehow learn to detect that and learn how to make a healthy one look unhealthy or vice versa? So one of the work here I'll show you is by, again, Julia, where they basically have an input image. They do the reverse steps to obtain, to go like to the noisy version, and then they denoise, but they will denoise only using, not everywhere, but they will push the denoising to happen towards, according to some classifier guidance. So they will use the gradients here of a classifier with respect to the desired class, the gradient, such that they can say, well, emphasize the changes more or less in this area. So by doing this, essentially, they're kind of deleting where the abnormality is. And once you do this subtraction, you're able to get an anomaly. Later on, Pedro from my team, they said, well, do we really need the classifier to do that? Why can we do this without the classifier at all? Why should we train a classifier for this? And basically what we do is that during inference, we have, let's say, the original image, and we train the model here that has a conditioning mechanism where we condition with information whether we want it to be healthy or not healthy, or zero, null, means I don't know, right? So essentially when we do this forward process, we arrive to a kind of like a state, a latent state, where there is ambiguous information whether this was disease or not. But then during the forward, like the forward process, not the reverse, during the forward, we say, well, now make it healthy. So essentially, this pushes out all the information about being healthy. It makes it healthy, pushes out the disease. So the subtraction of these two creates here a heat map that we can use for detecting the anomalies. You could see this image manipulation as an intervention of the factors that actually cause a change. So I use the word cause here, and I wanted to use this opportunity to introduce some of the work that we do with diffusion models in causality. Because we know very well that correlation is not causation, right? So if we want to make an intervention, like if we change, for example, the image from disease to healthy, we only want to alter the things that we should, but not other things and other aspects about the data, right? So here we wanted to come up with a model that is able to use diffusion models to create causally plausible counterfactuals. So to be able to ask questions of how an image will change if it to be classified as another class. Okay, I'm not going to go through all the details, but we use here the diffusion ordinary differential equations to estimate the latent space at time t. So the forward diffusion process, here we have a graph here, a causal graph, which is known with their endogenous and exogenous variables. These are the endogenous, these are exogenous. As we progress during the diffusion process, the forward diffusion process, we are actually kind of weakening the links here to be completely independent. So, and then if we go backwards, you make them dependent. So we use this kind of idea as a way to actually now do interventions. And we are able to say, if I cut here this link, can I change and create a new datum that is a change of this variable and how that will be affected. And the paper has full details. It was published in CCLR conference on causal representations and causal representation learning and causality. But the main gist here is that we're able to do, we look at the score of log conditional probabilities as a way to do it. But this work relies that we know the causal diagram. After we said, well, do we really need to know the causal diagram? Is there something else that we can do? So can we use, for example, diffusion models for causal discovery? So we say, let's say we have some variables D, A, B, C, D, and we have some samples of those, some observations. And our goal is to identify the relationship between these variables A, B, C, and D. So let's say here they have a causal relationship, as you can see on the right-hand side. So there is two things. Our goal is to basically discover these relationships here. Right? So we leverage here two key facts. That one fact is that this is a leaf, this B is a leaf, okay? That if it's a leaf, it will have a constant Hessian of the score, or a constant Jacobian of the score, okay? So, so this means that if I have a very quick mechanism to look at the Hessian of the log score, of the score, I will be able to detect whether somebody is a leaf or not, like one of the variable is a leaf or not. And I can do this in an iterative process. So we found that with the diffusion models, we can actually estimate the Hessian very, very quickly. And we also devised a metric that is able to tell us what happens if I make an intervention and I remove one of the variables. How will the score change without having to recalculate the score? And by doing this, we can now actually process graphs that are very, very large for the first time in machine learning using this type of estimation of the Hessian. So to conclude, I hope, I started with, something about what is generative models. Then we went to diffusion models, show you several examples on the medical image and medical image analysis frontier. And I showed you that they can even be applied even within the realm of causality. And causality, as we know, it's pretty useful, particularly in the context of health. So to go back to the question that I posed in the beginning, hype or hope. I think it's too early to say it's it's the de facto solution, and it will be everywhere in the clinic and so on. But at least the tremendous growth points to hope that we have yet a very strong arsenal as a tool as for us to learn and use machine learning in a lot of healthcare applications. And this is, I think, mostly due because of opportunities that we see with diffusion models, because they're very capable in doing data manipulations. And they're also to use kind of like a lot of fancy architectures that we developed all the time in the past, even from the GANs or VAs and so on, because they architect the inductive biases that we can develop. And the second thing is that they seem to be excellent integrators of multimodal information, whether it comes from text, images, measurements between, let's say, images in their case space and so on. But they're not without challenges, right? So one immediate challenge that arises is sampling speed. So you have to iterate, and there's lots of papers already now that are trying to accelerate how sampling is happening. And the second thing, I consider myself somebody who focuses on latent representations. It's not very clear where the latent space is. So in a traditional VA, we have very clearly that this is the latent space, the bottleneck, right? But what is the latent space? Is this, if I use a unit, is this the deepest part of the unit, the bottleneck in the bottom? Is it the noise in the latent space, the Z? Are the conditions the latent space? In all of these, somebody has done some work to show that they're a good alternative or not, but it's not very clear of where the representations are. So if you want to know more about diffusion models, I was able to populate here some surveys, GitHub collections, and tutorials. I will highlight the last one, which was actually came out last Thursday, and it's called A Survey of Diffusion Models in Medical Image Analysis. In fact, the reason why I wanted to do this talk, usually I give a talk on disentangled representations. I wanted to give this talk because I thought, maybe I'll collect enough information. It would be enough information to write a survey paper, but then I was gladly find that somebody else had done it before. Highly recommended, very nice paper. And the slides will be available in this link shortly as well. So without further ado, I would like to thank my team, and particularly Pedro for the help, my collaborators, and those who share a slide from all these different universities, my funders, and yourselves. Thank you very much.
Thank you, Professor. Now we will come to our attendees. So do you anyone have any questions? So if you have any questions, feel free to drop any questions to the professor.
Okay, I have a question. So thank you very much for the great talk. And I wonder if diffusion adversarial representation learning can be applied to natural images.
So I'll repeat the question. So whether the diffusion representation learning can be used in natural images, I would not say why not. I don't know if you're referring to that paper of Tolga where they use the adversarial mechanism to do that, but I think if I were to go back to the first slide where I showed you the progression of how things fast have moved in diffusion models, I would say comfortably that we are, here, this one. I would say comfortably that all of these works are not in medical image analysis, right? There are very few in medical image. Most of them are for natural applications. And if you were to look at some of the results of stability AI or DALI, now that you can access DALI, you will see that you can have impressive natural looking images. You can really control information. I think it's not by accident that Stable Diffusion Stability AI got a 1 billion valuation now. So I do believe there are powerful models. A year ago I didn't believe so, and I made a mistake not believing so. So I'm Pedro convinced me otherwise, and I'm glad he did.
Okay, thank you.
Okay, thank you. Does anyone have any questions? Not only from like the attendees in this room. If there are any other questions from our there's some. Wait a moment.
I have one. Can you hear me?
Thank you. Oh,
So I think there is somebody online. Jim, hi. Do you want to ask the question and then we can go
it's all right,
back
but
to
you
the
can
I
go
don't know what-
ahead. The person in Zoom.
I saw those. Very nice talk. Thanks.
Thanks.
Just a quick question, kind of. I mean, can you? I'm probably not familiar enough with the diffusion work fully, but can you think of diffusion as sort of a type of embedding space, right? And I mean, is there analysis about these spaces, about how they, might group in a statistical sense or some high dimensional space? And, is that helpful? Can you think about them in some more somewhat, I'll call it formal way, for lack of a better word?
Yeah, that's an interesting point. So we've done some investigations to see how and when diffusions, for example, separate, let's say, style from content, because my bias on the style and content stuff. There is some other work that look at the dynamics of how you can characterize the diffusion process with respect to its statistical dynamics, and identify, what's happening during the learning process, what's happening during the step of inversion, let's say, that time t here, right?
Yeah.
What are the transitions mechanisms? I think there is lots of work that has been done in terms of understanding something. The diffusion models, there's some of the first papers that came out were in 2015. And what happens here in 2021, there are two papers that came out that basically showed that they're much better to work by adding additional noise and denoising, right? So there was that one, and there was another one, the DDDIM by Dariwal, that had another trick. So I think if I were to plot the same graph for generative for GANs, right? And how we went and how we are now, I think I suspect a very similar, growth here of we identify even more and more about the theory of how they operate and what's happening during the theory versus the practice. So I don't have fully the answer, but I'm sure somebody will find it soon. Jim.
Okay, thanks. Yeah, it's interesting.
Then I cannot hear. There's a question.
Now?
Yes, I can hear you. Yes.
Okay, yeah, thanks for the talk. I was wondering how good the diffusion models are with the generation of hallucinations. Like, is that common, like with other generative models? And also in the case of anomaly detection, how robust are these models when, I don't know, like with interscanner variability, or just in general,
Yeah,
like
that's a good
patient to
point.
patient difference?
Yeah, that's very nice. So hallucinations, I think it's an interesting point. I yet have to see a good, let's say, empirical paper that compares several different generative models and say one is less can hallucinate. I mean, there are good hallucinations and bad hallucinations, right? So let's break the two. So if you refer to hallucination, the ability to generate data in the vicinity of others, like that's the extrapolation aspect. I think that's good hallucination. The hallucination of introducing, let's say, artifacts, like the checkered pattern that some of the GANs had. I think I haven't seen work that is able to demonstrate whether diffusion models do better or worse. I think that's something to be done. Overall, I don't think this is easy to do because we don't have yet mechanisms that can measure, is this an image good one or a bad one, right? I mean, without human evaluators, this is very, very hard to do. On the second question on the anomaly detection with respect to robustness, to scanner variation, or population variation. I think that's a very valid point. And most of the works that I showed you now are, I would say, in their infancy. So it remains to be seen how robust they are to domain shifts with respect to scanner strength and so on. And you know, and I'm sure it will be done very quickly. I think the way things are going now in machine learning, you know, by the time I say yes or no, somebody has done it. Okay.
Okay, thank you.
Sorry, due to the time limit, Professor, we will move to the next keynote
Okay.
speaker.
All right.
Thanks
Thank you very
again.
much. Thank you very
Okay,
much.
thank
And
you.
if you have further questions, please do email me. I'm easy to find in the University of Edinburgh. Thank you
Okay,
again for having me. I'll stay in the background and listen to the
Okay,
talks. Thank you.